Welcome to the Deep Dive. Today, we're really getting into the weeds, doing a bit of an architectural excavation.
Yeah.
We're looking deep inside a pretty complex application performance monitoring platform, an APM tool.
Right.
And we're using some specific insights, basically from certification prep materials, to really understand the core mechanics.
Sure.
The goal is to see what makes modern observability tick.
Exactly. So for you listening, think of this as cutting through the marketing hype.
Yeah.
We want to pull out those essential nuggets of knowledge, things about deployment, performance limits, how the platform stays resilient, and critically, those key admin functions that make it all work in the real world.
And look, we're not focused on passing an exam here. It's about understanding the fundamentals of these powerful systems.
That's the idea.
And maybe just for context, the source material we looked at, it's based on an exam format, 61 questions, need 41 to pass, 90 minutes. But that's just background.
Right. Just setting the stage. Let's get to the tech.
Okay, so first big challenge, scale. It always comes down to scale, doesn't it?
Always, especially with distributed systems.
You've got this massive flood of data metrics, logs, traces pouring in. It's honestly staggering.
It really is.
So where's the choke point?
Yeah.
What's the single crucial component that really defines the maximum potential throughput? How much can this ingestion pipeline really handle?
Well, it's interesting because you might think network or maybe the agents themselves, but the real architectural bottleneck is internal.
Okay.
It's the stream processor component. That's the key. It's configuration, how many resources you give it, that fundamentally dictates the ceiling on data volume.
Wait, the stream processor? Why specifically that? Why not say the database where everything ends up, or the gateway getting the data first?
Because that's where the actual, the heavy lifting happens in real time.
Okay.
The stream processor is doing the hard work, normalizing, correlating, adding context, aggregating all that raw data as it flies in. Traces, metrics, logs, everything.
So it's a compute bottleneck.
Exactly. It's computational.
Right.
If you don't give the stream processor enough CPU and memory, its queue just blows up.
Right.
And your real-time processing capability just hits a wall. It has to keep pace with everything your environment is throwing at it.
That makes sense. It's not just about receiving data, it's about processing it fast enough.
Precisely.
Okay, speaking of processing, let's talk about the platform's intelligence. The promise is often zero manual configuration.
The dream.
So if I spin up a new container, maybe running a JVM, boom, the system knows its Java, attaches the right sensor. How?
Yeah, that's not actual magic, thankfully.
Right. What's the mechanism? What's doing that automatic identification and attachment, the sort of real-time mapping?
That's the dynamic graph component doing its thing, along with its built-in auto-discovery engine.
The dynamic graph.
Yeah, and it's not just some static list. Think of it as a living, breathing map of your whole environment.
Constantly updated.
Millisecond by millisecond, yeah. Its engine watches OS signals, process lists. When something new pops up, it analyzes the signature JVM, Node.js, Python, whatever. And then it automatically deploys the right language-specific sensor package. Instantly. No human needed.
So the dynamic graph is this live internal map, and that map enables the continuous automatic discovery. Very cool.
That's the core idea, yes.
Okay, so the dynamic graph handles the magic, making monitoring seem effortless. But when the platform itself has issues, things get manual fast, right?
Oh, yeah, especially if you're self-hosting.
So let's say I am running this in my own Kubernetes cluster or on Docker. Where do I actually go for the hands-on stuff, like health checks on the back end, checking detailed logs for a specific service, or, restarting something?
That's a really important point about self-hosting. You're not managing the platform's own health through its fancy UI.
Right.
Since the back-end services in Instana's core components are almost always running as containers or pods.
You manage them through the container system.
Exactly. Your main tool becomes the system's container orchestration tooling. So kubectl if it's Kubernetes, or the Docker CLI. Those are your primary controls.
Okay, so you're using standard infra tools to manage the monitoring platform itself.
That's the reality. Inspecting pods, checking logs, scaling components. It's all done at that orchestration layer.
That's crucial for any admin to grasp. Sophisticated monitoring relies on pretty traditional foundations.
Absolutely.
Now, let's talk resilience, or maybe lack thereof sometimes. This is where those tools are either lifesavers or major headaches. Imagine a worst-case scenario. Data center loses power suddenly, everything goes dark.
Ouch.
System comes back up, but the logs are just full of errors about data partitioning consistency problems. Which huge backend bit is most likely the culprit here, needing complex recovery?
That scenario screams distributed time series database. That's almost certainly where the problem lies.
Okay, why that specifically?
Because that database, often something like ClickHouse, maybe Cassandra, in some setups, is storing all the fine-grained metric and trace data, and it's spread across multiple nodes.
Right, distributed.
So an uncontrolled shutdown, like a power cut, is poison for these systems. It risks breaking the consensus needed to keep data consistent and available.
It's not just like a simple corrupted file then.
Oh, much worse. You risk partial writes, sure, but the bigger issue in a distributed system is nodes potentially coming back up. Well, disagreeing.
Disagreeing about what?
About the state of the data, about who the leader node is supposed to be. You get these complex partitioning issues.
Yikes. So recovery involves?
It often involves running special tools to verify data integrity, maybe manually fixing leader elections, or potentially restoring the whole thing from a backup or snapshot, just to get accurate data correlation back.
Wow. That's significant operational burden.
It's the trade-off. It's the high cost you pay for managing your own highly available persistence layer.
Okay, that makes package management sound really appealing. Let's shift from complex failures to efficient routine maintenance.
Good idea.
We've got a big fleet of Linux VMs, maybe hundreds, all running the Instana host agent. What's the recommended simplest way to update that agent across the board?
Yeah, you definitely don't want to SSH into every box.
Please no.
So, assuming it's a reasonably mature setup, the best practice is to lean on what you already have. Use the operating system's built-in package manager.
Like yum or apt.
Exactly. Once you've done the initial agent install and configured the repositories, you treat the agent like any other piece of system software.
So you can use your existing config management or patching tools.
Right. Push updates centrally, automate it. Much less manual work, much lower risk.
Okay, that flows nicely from operations into integration. Any modern APM tool has to play well with others, right? It needs to fit into the existing ecosystem.
Absolutely essential.
So let's say I have some older system or maybe a custom app, and it's already spitting out monitoring data in a common format. Is there a popular open standard that Instana can just natively consume through its sensors to make integration easier?
Yes, and this is a big one for avoiding vendor lock-in and simplifying rollouts. The platform has native support for ingesting data in the Prometheus metrics format.
Oh, Prometheus, that's huge.
It really is, because Prometheus is pretty much the de facto standard now for cloud-native metrics.
So what does native support mean practically?
It means you can point Instana at anything exposing Prometheus metrics using standard exporters, and it just ingests them. No need for complex translation layers or custom code. It simplifies things dramatically.
Makes sense. Interoperability is key. Okay, let's pivot slightly from data formats to data integrity.
Okay.
I feel like this next one is maybe the single most critical setting, but it often gets overlooked. It underpins the accuracy of all the trace data we're collecting.
I think I know where you're going with this.
What single infrastructure setting must be correct across all your monitored hosts, all your servers, to guarantee accurate trace correlation and event sequencing?
Yeah, if you think about the whole point of APM effective root cause analysis, then this is absolutely fundamental.
It is.
All devices must be synchronized using Network Time Protocol, NTP, period.
NTP. Why is accurate time so non-negotiable here?
Think about how distributed tracing works. It's about stitching together tiny event spans that happen across potentially dozens of different services on different machines.
Right, microseconds matter.
Exactly. If the clocks on those machines drift apart by even a few milliseconds, forget it. The back-end system completely loses the ability to accurately reconstruct what happened when.
So time drift just breaks the correlation logic.
Completely. You can't reliably link logs to traces. You can't figure out the true sequence of events in a complex transaction. NTP sync is the literal backbone of accurate distributed tracing. No excuses.
Okay, so we've got data flowing in, it's synchronized, the dynamic graph is mapping everything. Now, the admin needs to make sense of it all from a business perspective.
Right, translating the tech view into something meaningful.
How does an administrator logically group things together? Define the boundaries of what constitutes a business application, making sure all the right microservices, databases, front ends are included for consistent reporting.
Yeah, in today's world with microservices everywhere, static boundaries based on IPs just don't work well.
No, things move around too much.
Exactly. So the flexible way, the recommended way, is defining rules based on metadata within the telemetry itself. things like traces, specific HTTP headers, or tags.
So using information already in the data flow.
Precisely. Maybe there's a shared HTTP header identifying the originating client, or a common tag applied by your deployment system, like app.billing.
Oh, okay.
By using rules based on that metadata, you ensure that no matter where a component is running, if it has that tag or header, it gets grouped into the correct logical application view. It's much more robust.
Yeah, much better than relying on fragile network ranges. Okay, let's talk control and security.
Important stuff.
Before an organization goes through the whole process of integrating with, say, Enterprise LDAP or SAML for authentication, they probably still need finer-grained control internally, right?
Definitely.
Like maybe letting the dev team see production metrics but not change anything, read-only access for specific teams. How does Instana handle that? What feature allows for those granular permissions?
That's handled through the platform's built-in role-based access control system, usually called custom roles and permissions, or just RBAC.
Or BAC. Okay.
Yes, standard concept. It lets administrators create very specific roles like prod read only or staging admin and define exactly who can view what, configure what, or modify what.
And that applies to different parts of the system or specific applications.
Correct. It gives you that essential detailed security and separation of duties before you even think about integrating with bigger, more complex external identity providers.
Makes sense. Get your internal house in order first.
Always a good idea.
All right, last challenge. The ultimate headache for traditional monitoring agents, serverless.
Ah, yes. Face environments.
Specifically things like AWS Lambda. There's no persistent OS to install an agent on. And manually adding monitoring code to every single function, that's just not scalable.
No, absolutely not. It defeats the purpose of serverless agility.
So how do you deploy the agent effectively in these environments to get tracing and metrics without developers having to touch every function's code?
The serverless world definitely required a new deployment model. The standard solution is to use the Instana-provided layer or extension that's specific to the cloud environment.
So for AWS Lambda, that would be a Lambda layer.
Exactly. You deploy the official Instana Lambda layer. This layer then automatically wraps around each function instance when it spins up.
Wraps around it.
Yeah, it essentially injects the agent automatically at runtime. It instruments the function, enables tracing, collects metrics, all without the developer needing to manually add Instana code to their function.
Clever. So it maintains that promise of automatic, autonomous discovery, even for these super short-lived, ephemeral things.
That's the key. It brings that same level of visibility without breaking the serverless development model.
So maybe a final thought to leave people with.
Yeah, let's think about the kind of operational paradox we've touched on. On one hand, the monitoring experience is designed for maximum automation, right? The dynamic graph finds things, serverless layers auto-instrument. It makes the observability part incredibly efficient.
Right, that's the selling point.
But then, the operation of the backend platform itself, especially when self-hosted, feels, well, surprisingly traditional and complex sometimes.
Like managing those distributed databases that hate power outages.
Exactly. Or relying on low-level Kubernetes commands, the CLI, for day-to-day admin health checks and fixes. So the question, I think, for you to ponder is, how does that efficiency gained from auto-discovery and all the smart monitoring features balance against the inherent complexity needed to actually run and maintain the platform itself?
Yeah.
How much operational heavy lifting are you or your organization willing to take on to get those autonomous monitoring benefits? That trade-off really dictates whether self-hosting this kind of powerful platform is the right move.
That's a really sharp way to frame the decision. A perfect reflection on the realities behind the slick interfaces. Thanks for joining us on The Deep Dive.